Oh, right, today we're going to go through the specimen paper for Equilibria, energetics and elements. So this is a slightly unusual paper. As you know, the papers do change over the years, but it's good practice for us anyway. So let's kick off with question 1. Right, so we'll start off with question 1. This is a nice rate question that we're going to look at. I'm just going to shimmy the board up to give me a bit more space. Now, I need to work out the order with respect to ozone and C2H4. So let's do that. If I look at experiments 1 and 2, hopefully you can see that the concentration of ethene remains the same. However, if I go from 0.5 to 2, I'm timesing the concentration of ozone by 4, and I'm also timesing the rate by 4. So from experiments 1 and 2, if the concentration of ozone is times by 4, the rate is also times by 4, and therefore it is first order with respect to ozone. The next one's a little bit more complicated. Let's have a look at experiments 2 and 3. If I'm just going to ignore ethene for a minute, if I go from 2, I'm timesing the concentration of ozone by 2. So I'd expect, based on ozone doubling, I'd expect the rate to double. So I'd expect it purely based on ozone to be 8. However, it's 16. So if I now take this into account, if I times that by 2, I go from 8 to 16, so I times the rate by 2, and therefore it is first order with respect to C2H4. So from experiments 1 and 2, if ozone is times by 2, the rate would also be times by 2 to 8.0 times 10 to the minus 12. If I now multiply the concentration of ethene by 2, the rate is times by 2 from 8.0 times 10 to the minus 12 to 16.0 times 10 to the minus 12. And therefore, it is first order with respect to ethene. Right, so I've done that. Let's do my rate equation then. So therefore the rate is the rate constant times the concentration of ozone and the concentration of ethene, like so. For the next question, I need to calculate the value of the rate constant and state the units. I've got the table up on the board because I'm going to use that data. So we know from the last question that we have this as our rate equation. So I can rearrange that the rate constant is equal to the rate divided by the concentration of ozone and the concentration of ethene. I'm going to use experiment 1 to do that. The key thing to remember is to check here. So it's 1.0 times 10 to the minus 12. These two concentrations, that's 0.5 times 10 to the minus 7, multiplied by 1.0 times 10 to the minus 8. So, as ever, I'd recommend you do this first. Sometimes if you try and rush it, you make a mistake, and on this paper you really don't want to lose marks just because you haven't popped it into the calculator correctly. That gives you 5.0 times 10 to the 16. So let's do this now, and that gives me my answer as being 2,000. I now need to work out my units. Rate is in moles per decimeter cubed per second. Concentration is in moles per decimeter cubed, and I've got 2 times that squared. That's going to do that. So it's going to end up being moles to the minus 1 decimeters cubed seconds to the minus 1. Right, so the next question is actually quite simple, but it does confuse people. Using equation 1.1, deduce the initial rate of formation of oxygen in experiment 1. So let's go back. It's told me I've got to use this equation and experiment 1. You've got to read the question. The rate of reaction was investigated, blah, 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 by measuring the initial rate of formation of methanol. So I measured the rate of formation of that. Notice for every 2 of those, I make half a mole of that. So it's 2 to a half. Or, if you want to times everything, it's 4 to 1. If you don't mind working, just do the question. So how would you get rid of that half? You times everything by 2, wouldn't you, to give you that? Sorry, to give you that. So it's 4 to 1. So if I measured the rate of formation of that, I only make 1 mole of that. So I'm going to take that and divide it by 4. So the initial rate of formation of oxygen is equal to 1.0 times 10 to the minus 12 divided by 4. So if we do that, 1.0 times 10 to the minus 12 divided by 4 gives me 2.5 times 10 to the minus 13 moles per decimeter cubed per second. So the experiment was repeated at higher temperature. How would the new conditions affect the rate of reaction and the value of the rate constant? So as we know, if I increase the temperature, the rate of reaction will increase. So rate will be faster. How will the rate constant be affected? Well, if the rate's faster, obviously the rate constant must be larger. Because if we go back to my rate equation, rate is equal to the concentration of ozone times the concentration of ethane. I've altered the temperature and the rate's gone up. We know that from GCSE. I haven't altered these two concentrations, have I? I've only altered, so therefore that rate constant must be larger. Rate constants are affected by temperature. Okay, nitrogen monoxide involved in formation of ozone, yep, we know that from AS. Gives me 3 reactions and I need to write the overall equation for that. There's different ways to do it. You can add all 3 together and cancel out, or you can do it a little bit faster. I use that there, but I produce NO there. So those 2 can cancel because they would be, when I added it all together, they cancel each other out. NO2 is on the left and on the right, so that cancels out. What else am I left with? I've got O2, O there, goes with O there. So I'm left with half O2 plus O2 goes to O3, or 1.5 O2 goes to O3. What's the catalyst? Well, the catalyst is going to be NO. Why is that? Well, it's because it's used in the first step, used in step 1, but reproduced or reformed in step 2. I use it there, I reproduce it there, so it keeps cycling the reaction around. Right, so that's question 1 out of the way. Let's move on to question 2. Bronzed lauric acid is a proton donor. A weak acid partially dissociates in solution. Phenol is being mixed with sodium hydroxide, acid-base reaction. Label one conjugate acid-base pair and then the other. So, if we look at phenol going to phenoxide there's a difference of H+. So that is acid 1 and that's base 1 because he's lost the proton. If he's acid 1, he's got to be base 2. He's accepting that proton to make water, so he is acid 2. These two differ by H+. The one with the extra H+ is the acid, the one missing the H+ is the base. So, solution of phenol water has that concentration. Write an expression for the acid dissociation constant, Ka. So first of all, let's just write the equation to make sure we get this right. C6H5O minus plus H plus. So Ka is going to equal H plus aqueous times the concentration of phenoxide aqueous over the concentration of phenol aqueous, like so. Calculate the pH. First thing to notice, they've given me the concentration in grams per decimeter cube. That ain't no good, so I want the concentration of phenol in moles per decimeter cube. So it's going to be 4.7 divided by the molar mass of phenol. If you can't add all that up, that gives you 94. So that equals 0.05 moles per decimeter cubed, first of all. I now need to calculate the concentration of H+. To do that, it's the square root of Ka times your concentration. Ka, they told me, you just bear with me for a minute, it's up here, 1.3 times 10 to the 10. So that equals the square root of 1.3 times 10 to the minus 10 times 0.05. So we just whiz that in, times 0.05, square root it. That gives me 2.55 times 10 to the minus 6. Now I can do that into my pH, which we all know. So it's minus log to the base 10 of 2.55 times 10 to the minus 6. Let's log that, change the sign. That makes it 5.59